Let's summarize what we learned in our exploratory lab. If we send a ray of light from the air into a dense material like glass, the light will bend when it enters the material. So you can see here that the light is actually changing direction when it goes into the material. It could have gone straight over here, instead it's going this way. There's also a reflection, but we're not too concerned about that at the moment. Now, if I shoot light from glass into air, then light's coming from the glass, it enters the air, and it bends in the other direction. If we make an imaginary line right down here in the middle, then from air to light, it bends toward that imaginary line, toward it. It would have gone this way, but it kind of bent toward it. And if I go from glass to air, it bends away from this imaginary line right here. It bends away from it. Now finally, we also noticed that if you go from glass to air, and this only works from glass to air, or some dense material to air, at a super big angle, that the light doesn't actually refract, it just reflects right off here as if this were a mirror. And of course, it's not a mirror. It's kind of weird because this is transparent glass. So it's interesting that it's acting like a perfect mirror, keeping all the light in. This is called total internal reflection. And it only happens when you're going from glass or a dense material into air, never when you're going from air into glass. Let's summarize what we learned on a nice diagram. So here I've got air and glass. I know that if I take my laser and shoot it from the air, that it bends kind of this way toward an imaginary line right here, and it bends that way into the glass. So let's sketch this out. This is the surface between air and glass. I'm going to draw in an incoming ray of light from the air. Does that look about right? Now, I draw in my imaginary line. Remember, I always talked about an imaginary line right here. Well, I'm going to draw in a line that's at right angles to the air glass surface. So right angle is something like this right here. And I'm going to draw it right where the ray of light actually hits the glass. So at a right angle to the surface of the glass. And I'm going to draw that as a dashed line, just so I don't confuse it with all the other lines that I've got. Now, does that look like about 90 degrees? I hope so. I think it does. We have a special name for this line. We call it the normal line. Not because there's an abnormal line, but normal is another word for perpendicular, which means 90 degrees. That's the angle. So we're just going to have to put up with this vocabulary. Now, if you remember, when we shot our laser in, it bent toward the normal line. So if refraction didn't exist, the light would go straight along this ruler, but it's going to get tilted toward the normal line. So tilt toward the normal line, just like that. I draw in my resulting ray. Goes off in this direction, because it's bent toward the normal line. Let's see, does that look about right? If I put my glass here, I shoot my laser down here, and oh, look at that. It's doing exactly what we've drawn right there. Perfect. Now let's do the same thing for shooting light from glass into air. And if you remember, I took my laser. Here's the light's coming from the glass, and it enters the air, and it seems to be bending. It's not going straight, it's bending that way, away from the normal line. So here's the normal line, it bends away from it. So let's sketch that out. Here's my incoming ray of light. I need to sketch in the normal line. If you remember, I make the normal line at a right angle to the air glass surface. Right here, and I make it right where the light hits. We like using dashed lines so we don't get all confused. normal line. Now, the rule is that when light goes from glass to air, it will bend away from the normal line. So this is the path the light would have took if it were to go straight. There's the normal line. I want to bend it away from the normal line. Go away from that normal line. So the light comes out there. Let's see, does this all make sense? Does this all work? Let's give it a test. Here it goes. Is it going to bend away from the normal line? Yes, indeedy, and I've got that pretty close. Not bad for just guesstimating. So, let's sum up here. If light is going from air to a dense material like glass, I'll just call it air to a dense material, this could be glass or water, whatever, then it will bend toward the normal. Line. If instead it goes from a dense material into air, then it will bend away from the normal. And there is your summary. You might want to pause the video here and make sure that this is in your notes. Wouldn't it be nice to know exactly how much the light bends? So if we knew the angle which this is coming in at, and we knew what material it was going into, we should be able to predict exactly where the light is going. And lo and behold, we can do that. And here's how we do it. This angle right here, from the normal line to the laser beam, is called the angle of incidence. The angle of incidence. And this angle from the laser beam to the normal line is called the angle of refraction. Right? Makes sense. The light is incident upon the glass here, and then it refracts. So this is our angle of incidence, this is our angle of refraction, and we always measure it relative to that normal line, which is so important. Now, we can use our theoretical graphs to predict exactly how much it's going to bend. So I have a graph here, light refracts from air into glass. Very useful title. And you can see that there's a graph, there's some numbers on here. So if we know, say for example, our angle of incidence is 50 degrees, we go down to angle of incidence, which is clearly labeled on the x-axis, there's 50 degrees. We go up here to where it meets our graph, our line, and then we go over and we see, okay, what's our y value right there? Oh, it's 30, which is our angle of refraction. So voila. If this is 50 degrees, then we know that this is 30 degrees, and we can find it on our graph. All right, now go do it.